right at stoichiometry. Usually, if you're a little bit lean, you burn up all the oxygen. I'm sorry, if you're a little bit, yeah, if you're a little bit rich, you burn up all the oxygen. If you're a little bit lean, you burn up all the fuel. And usually, a lean burning flame will burn a little hotter. And the presence of inerts, which if you're burning in air, you've got 4 moles of nitrogen for every mole of oxygen, roughly. We also said the gas boundary layer greatly limits the actual heat transfer to the surface because you end up with a cool layer of the gas boundary layer being cooler. The heat has to diffuse across a thermal boundary layer of that more stagnant gas. And somehow I got into doing a quick estimate of what types of maximum temperatures you can get in a air burning flame, and I think I got mixed up, mostly because I'm going to have to go back and read my World Trade Center paper. I wrote it and I said, gee, you get about 1,000 degrees increase in temperature. And then I got an email from someone a few weeks later. Some MIT grad said that he liked the paper, but I made a mistake. I should have been working in degrees Kelvin rather than degrees centigrade. And I wrote back and said, yeah, you're right. But I didn't spend a lot of time thinking about it. But I started thinking about it on the plane yesterday, and I decided, no, I think I was right. And I think I did it for you wrong yesterday. It's actually delta T of the flame that we're interested in. It's not T, absolute temperature. It's the difference in temperature. And delta T centigrade and delta T Kelvin are the same, okay, because the measurement of the degrees are basically equal, right? So if the delta T of a flame in pure oxygen is 3,000 centigrade, well, actually, if the calculated, actually I take that back. I think the calculated delta T is going to be, or the T of the flame calculated is 3,000 centigrade, which is about 3,300 Kelvin. The delta T is about 2,700 centigrade because you start out with your fuel and your oxygen already at around 300 centigrade, room temperature, or 300 Kelvin. So delta T should be, I was doing this morning, I should have done it on the plane. Anyway, that's around 900 centigrade as a delta T because I've got to carry around 3 times as many moles. There's 2 moles of nitrogen for every mole of gas reaction product. And we did that yesterday. And so that brings us up, that's going to be 1652 Fahrenheit for a delta T of a hydrocarbon in air. Well, forget about this one. Okay, so that's a estimate of what the delta T of a fuel burning in air is going to be. I think I've done that right now. And you have to keep track of whether you're delta T or T. Yep.
You said that you start at 300 degrees centigrade?
No, it was 300 Kelvin. You're right. Yeah, I'm sorry. Okay. And then what I wrote down before class was right. You're right. This is center. It's you're right. Forget that I was right the first time, and I wrote it down. You're right. I'm not 300 centigrade. I like the 1832 better. So this is 3,000. So you're right. So it's 1832 Fahrenheit is the delta T. If I did it in Kelvin, I have to add on the 300 degrees to get to Kelvin. Then I divide by 300, divide the 3,300 by 3, and I get 1,100. But then I have to subtract off. Actually, how much do I subtract off? 300.
3,300 and delta T is just 3,300 minus 300. So you got to start at 3,000.
Yeah, it all works out the same. Agreed. Okay. That's what I figured out yesterday, and that's what I was trying to do this morning. But it is a delta T you're talking about, and I think maybe the person who criticized my paper, I have to go back and look and see if I did it wrong in the paper. Anyway, it's just an order of magnitude calculation. And the point is, you can't get temperatures of 2,500 degrees Fahrenheit necessary to melt steel in an air burning flame. you have to do some preheat of either your fuel or your oxygen. Okay, and there's various ways to do that. Yep.
Lean flame is one. When you say lean, are we oxygen lean or fuel lean?
Your fuel lean. Usually, when you talk about lean, you're talking about not enough fuel. Rich is you're burning excess fuel, and lean you're burning excess air. If you burn usually on an engine, if you make it run lean, it runs hotter, and you burn up your valves quicker. So a lean burning engine, and the reason for that is you have some excess oxygen, and the excess oxygen has a lower heat capacity than excess fuel. Excess fuel are more complex molecules and have higher heat capacities. In all of these types of rough calculations, I'm assuming everything's an ideal monatomic gas, or they're all diatomic gases, but there's no differences in heat capacity. In fact, there are differences in heat capacity. And a complex molecule like fuel has lots more vibrational modes and has a higher heat capacity than oxygen, which is a diatomic gas. So you can refine these things, but order of magnitude, you ought to be able to figure out you can't get 1,500 degrees centigrade, 2,500 degrees Fahrenheit in order to melt something like steel, just by starting with things at room temperature. You've got to preheat things if you're going to get things really hot. Okay, any questions on any of that? I want to talk about basic types of flames. The first one is a diffuse flame, and a diffuse flame is basically what you see in a fireplace or in a bonfire. In a diffuse flame, you've got some fuel and some oxidant, and they don't really come together except when in the atmosphere, and they have to diffuse together. So you get kind of wispy flames that kind of bounce around back and forth like a bonfire or a flame in your fireplace. And the temperature of a diffuse flame is going to be lower than the maximum temperature because you're not burning at the stoichiometric ratio. You're burning at the lowest ratio of oxygen to fuel that will support combustion. And that's not going to be the stoichiometric ratio in general. For example, if you look at flammability limits on different materials, acetylene has a flammability rating from like 3% acetylene in air to 80% acetylene in air. So that's why acetylene is sort of a dangerous gas. It'll in almost all combinations with air, you can get a flammable mixture that's going to burn. Now, if I take methane, CH4, its flammability rating is 6 to 16%. It's not easy to blow your house up with natural gas. People can sometimes do it, but it's not easy because you have to be in a very narrow range to support continuous combustion. At the lower end of the flammability limit, you don't have enough fuel to generate enough heat to heat up all the inerts to keep the process going, and so the thing essentially puts itself out. At the higher end, you've got too much fuel, and now you're going to put yourself out because you're not generating enough heat overall to keep it going. You've got too much excess fuel that's absorbing the heat. So there are flammability ranges of things, and you can look these up in a typical gas handbook. Now, when you look it up, be careful. Flammability ranges are usually at 1 atmosphere pressure and at room temperature, and on a sunny day when someone just sold a hot dog outside on the street corner. I mean, there's all kinds of conditions that go into flammability ratings. But nonetheless, there is a difference, significant difference between acetylene and methane and propane. Propane is even more difficult to get an explosive mixture in air because it's even more complex molecule than methane, and so its flammability limits, I think, are like 8 to 11% in air. They're fairly narrow. There's also flammability limits, there are explosive limits, and that just has to do with how Okay, in any case, the diffuse flame has, you got it? You got it? Okay, the diffuse flame has a fairly low speed, and you can see the flames as they whisk back and forth. If you go to a premixed flame, And by the way, you can have a diffuse flame where you're just shooting fuel through a burner and the oxygen has to diffuse in from the sides. In a premixed flame, you actually mix at constant, you mix the gases in the chamber and then they shoot out and they burn in the atmosphere but at constant pressure. You've got 1 atmosphere pressure. It turns out the, that should be 10 times, it should be 10 to 100 times the velocity of a diffuse flame in a premixed flame. And I'll pass this again around again in just a second here. I do want to turn it on again. If you look inside this thing, you take this off, unscrew this, you can see some little turbulators in here. You also, on the end, this is piezoelectric start. You'll notice that the nozzle is actually doing something. This thing doesn't want to keep burning when it's just coming out a great big hole here. It actually has a nozzle and it has some little fins in here. And also, when I pass it around, I'll take the gas tank off, but you can see inside, you'll see a little spark. This is a piezoelectric thing in here. If you hit it mechanically, it gives off a high voltage spark of several thousand volts. If you've got a gas burner on your stove at home, typically they have piezoelectric starts. You flip it to the start and hear tap, 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 tap. There's something in there mechanically hitting a piece of ceramic that gives out thousands of volts. So this has got a turbulator in there that tries to produce a swirl that gives you a nice proper velocity on your flame. Turns out this tube is probably a piece of Inconel, which probably costs about $30 a foot. So you got about $6 or $7 worth of tubing right here. Inconel's a nickel-based superalloy, high nickel chrome alloy that takes a lot of heat. Now, hopefully things don't get screwed up, but if you had low pressure, the flame wouldn't be coming out as fast. This torch is designed for a certain velocity, and the nozzle is designed for a certain velocity. And you notice that it's thinner down here than it is up here, and that's because they started a swirl to try to bring things together and they designed the combustion to go right. Now, if you're careful, and I don't know if they'll hear it on the video, but when I do this and I turn it off, you hear a pop back. You heard that? The secondary pop. Anybody know what that is? It's called flashback. And what happens is when I have proper pressure in this thing, it's designed so that I get the proper velocity coming out. When I shut it off, the gas is being shut off and the velocity has to drop to 0. Well, there's a certain burning velocity of the gas depending on the stoichiometric ratio and whatnot. And so this thing is designed not to be burning in this chamber right here, but just be burning, or essentially be pushed out. If my pressure goes down, the flame is going to pull back inside here. And what happens when I actually shut the whole thing off and I get that final little pop, what's happening is it's coming back here and there's a little burning right back. You don't see it on this one because it's designed, it's got what we call a flashback arrestor in here. But the final combustion is actually inside the chamber back here. And so the last gas, as everything's slowing down, the burning front comes back down in here and then ignites finally in a final combustion back in here, and that's at constant volume, so you hear a little pop, and what you're getting is a little breeze coming out the back end. Okay? In fact, actually, I saw it that time. You can see a little flame right in those holes. If you look careful, quickly. So if you want, we'll pass it around and you can make noise yourself. If you want to take, well, actually, you can't do both of these at the same time. You got to either take this off. If you want to see the piezo, why don't we do that? It's safer than letting you all. If I burn down the classroom, at least MIT, I'm employed by MIT. But if you want to see the piezoelectric thing, the little spark there, that's what ignites it. So why don't I just pass those two around again? You can have that. You don't have to burn yourself up with this. So that's flashback. And inside that tube, I can't disassemble it. I tried this morning, and I don't want to destroy it. By the way, that little torch goes for about 40 or 50 or 60 bucks. And it's partly because of the Inconel tube and the piezoelectric starter big profits and things like that. But nonetheless, there's actually a fair amount of technology that goes into designing one of those things. You don't just gotta make a simple one yourself. You gotta get the orifice size, that little hole where the gas comes through, proper. You gotta get the size of the holes to let the oxygen in proper to get the right mixture ratio. If you don't, you're gonna end up with incomplete combustion. So that's a pre-mixed flame. It's designed to give you a nice blue flame, no excess soot, which is going to turn the flame yellow, and things like that. You're going to get a higher burning velocity because you have a higher temperature. You're at the stoichiometric ratio as compared to a diffuse flame. You're burning at constant pressure, and so it's not too loud. Now, the third type of basic flame is called the jet burner, and actually premixed flames are useful in welding and brazing and soldering, but jet burners are generally not so useful. In a jet burner, in welding and brazing, but they're useful in things like flying airplanes. You bring fuel in, you bring oxygen in, and you ignite it inside a chamber at constant volume. So all your PDV, now it's a VDP, okay, you're going to end up increasing the pressure because you're at constant volume. So instead of PDV in the diffuse flame, in a premixed flame, you have a VDP, increase the pressure by 5 to 10 fold, and that's going to give you 5 to 10 increased velocity coming out because of the increased volume of the gases in here. That's a jet burner, and I don't have a jet burner to demonstrate, but you've been next to a jet engine and you've heard the noise because of the higher velocity of the gas coming out. Higher velocity of the gas means a greater heat transfer rate. If I go back to these three things and I wanted to look at heat intensities, a diffuse flame, typically burning in air, but even if you had one diffused burning in oxygen, a diffuse flame will give you something on the order of 1 to 30 watts per square centimeter. Sometimes less, sometimes a little bit more, depending on the diffuse flame. But a candle is like 1 watt per square centimeter. I mean, you can put your finger through a candle at a nice slow rate and not burn yourself. Not too slow a rate, but you're not going to burn yourself. Now, what's 1 watt per square centimeter? The sun, on a bright sunny day, is something like 0.03 watts per square centimeter. So you're 30 times higher than the heat intensity of the sun. So you can burn yourself. If it takes you an hour to get a sunburn, if you're fairly fair skinned, it would only take you 2 minutes to get a bad burn in a 1 watt per square centimeter flame. Actually, you might get a little quicker than that, but because the burning is a little bit different type of burning. But nonetheless, this is 1 to 30, let's say. A premixed burning in air might be anywhere from 10 to 100 watts per square centimeter. I'm sorry. A premixed is gonna be well, it might be up burning in oxygen. You can get up to about 100 watts per square centimeter. I'm sorry. 1,000 watts per square, yeah, that's right. So, in premixed in air is 10 to 100 watts per square centimeter. In oxygen with acetylene, I can get up to 1,000 watts per square centimeter. With a jet burner with a higher velocity, I can get up to about 2,000 watts per square centimeter. So there's fairly wide ranges here depending on the actual velocity and the size of the flame and the type of gas and stuff. But the intensities of a diffuse flame, let's face it, if you had a house fire, the flames are not usually going to be more than about 10 watts per square centimeter. And that's plenty to give you a sunburn or burn you and whatnot. But it's not going to melt steel or copper very well. It won't melt either one of them because it doesn't get hot enough in air. But even aluminum, which it might get hot enough to burn, to melt, it's going to take a while to do it. It's not going to melt in the first couple of minutes.
Do they use jet burners to cut metal?
No, it's a little bit different. I'll talk, well, they do as plasma torches, but I'm going to talk about that later. The main application for jet burners other than jet engines, Jeff, another question?
Yeah, just a question about the melting. I guess I can understand why it wouldn't melt in terms of surface melting.
Right.
It didn't have very heat intensity. But if you kept it in the flame long enough, the whole thing heated up, could you potentially melt it just by heating up the whole bulk of it?
You can heat the whole bulk. You can melt aluminum because if I got a temperature here of 1832 by burning in air, so if I put aluminum inside a typical premixed flame, at stoichiometric ratio, I'm going to melt the aluminum. But it may take a fair amount of time because I'm only putting it in at 10 or 20 watts per square centimeter. And the actual heat intensity or the heat capacity of that is for, let's see, if I remember, a cubic centimeter of typical metal, if I remember correctly, has like 6 kilojoules of heat capacity or something like that. Well, 6,000 joules at 10 watts per square centimeter is going to take 60 seconds. Okay, about a 1 square centimeter surface into something like that. So it's going to take some time for all this to occur, to build up the heat. It's not going to melt instantaneously because I'm at too low a heat intensity. But you're right, if it's completely surrounded and the flame temperature is high enough. Now, let's take another example. You know that aluminum doesn't melt in a diffuse flame. And that's because it's not at 1832 degrees Fahrenheit. Okay? It's at a lower temperature because I'm not at stoichiometric ratio. And you know that aluminum doesn't melt in a diffuse flame. How do you know that? You ever been on a cookout with the Boy Scouts or the Girl Scouts and people use aluminum foil dinners? It wouldn't be very good if you melted your aluminum foil all on top of your dinner, right? So you actually don't even get hot enough to get to aluminum melts at 660, which is centigrade, which is what, 1220 Fahrenheit or something like that, okay? So if aluminum melts at 1220 Fahrenheit, the bonfire is probably at 1,000 degrees Fahrenheit or 1,100 degrees Fahrenheit maximum. You don't melt the aluminum. You might oxidize it away. You leave aluminum foil on the fire long enough, and it'll oxidize away and crumble on you, but it's not going to melt. Now, let's take an aluminum frying pan on your pre-mixed burner on your stove. That flame is actually hot enough, that nice blue flame is hot enough to melt the aluminum, but in that case, I actually have a radiating away top surface and a bunch of side surfaces. If I had a huge burner that completely covered the bottom of the pan, and I left it there with no water in it to help evaporate everything, cool things off, then I could potentially melt an aluminum pan on a pre-mixed burner of a stove. I can't melt copper and I can't melt stainless steel because I just don't have enough heat, don't have enough temperature. So it's both the absolute value of temperature and heat intensity. The heat intensity determines how long it takes to heat up, and the temperature tells you whether you actually can reach a temperature sufficient to melt. And if you just think about what happens to aluminum in bonfires, on the top of your stove, you actually could potentially, if you left the bare aluminum pot on the stove and it was a very small pot on the big burner, you could potentially melt it, except you have the problem of the aluminum's radiating away. Now, if you put a propane torch on the top side, yeah, you've now covered the whole thing, and it's not going to be radiating away on one surface. It's not going to be heated on one surface and radiating away on two surfaces, and therefore, if you're heating on both surfaces, you're going to be able to melt it. Okay, because aluminum's right on that edge, okay, of temperatures that you're probably going to get in many of these flames. Now, jet burners, yeah, you can melt aluminum with jet burners, and the biggest use of jet burners, of course, is in jet engines. But there are commercial uses in things like drilling holes in rock. It turns out that jet burners have been used for 50 years or more to drill holes in rock. Now, they quit doing it for a number of years, but what happens is if you're at the bottom of, or I'm going to actually have the hole started in the rock, and this little layer right here of rock at the bottom of the hole, and I've got a jet burner shooting in here with 2,000 watts per square centimeter. With a typical thermal conductivity of granite or something like that, it turns out that I'm going to heat up just a 1 or 2 millimeter and it's going to expand. And if it expands, what happens to a brittle ceramic? It's going to crack. And so this little layer right beneath at the bottom of the hole will crack up into a bunch of little pieces, form small little cracks. I've got this jet burner where the velocity is 500 meters a second. I mean, it's basically heading towards supersonic. Jet burners are extremely loud. They get to this type of jet burner, but even jet engines and stuff. If you are right behind one and they don't Right now they're a lot quieter than they used to be, but if you were right behind one and they didn't have a lot of the noise control things on it, you would typically get values of 140 to 160, and even in some cases approaching 180 decibels. Now, 180 decibels, I think 160 to 180 decibels is getting to the threshold of pain. I mean, you can start, it's not just damaging your ears, it's getting to be painful to even be in something, you know, your ears will start to ache at that point. Which is one of the reasons they quit using jet burners for drilling rock. But at that type of heat intensity, you're basically expanding this faster than the heat is transferring out to the other sides. Because I have a low thermal conductivity material, I crack it up into little pieces, and the little pieces get blown out with the wind. And it turns out you can drill through rock, hard rock, faster with the jet burner than you can drill with a mechanical drill. And so back in the 50s and 60s, when we didn't have OSHA to worry about people's long-term hearing, they used to use jet burners all the time. And sure, people use ear protection, but it wasn't the best ear protection. And people who worked in this business would go deaf, basically. Then OSHA came along, and they basically, because of the environmental controls and concerns, they basically went back to manual, mechanical drilling of rock. In recent years, because of the higher productivity, they've actually started paying for the sound protection and automation and things like that, so people aren't as close by. Obviously, sound decays as you go further away. And so now they have, in certain cases, you're not going to see people drilling rock in an urban or suburban area with a jet burner. But if you're out in the middle of a mining district or in the middle of some rural area, and the only people you're going to hurt are the cows, okay, in the fields, people don't care if the cows go deaf. I mean, the beef sells the same way, okay, if the cow has hard of hearing. Farmer may not like his cow being hard of hearing, but in any case. So they have been going back because of the higher productivity. Just another kind of example of, as we improve the environment for workers, we quit using certain technologies, but the higher productivity, eventually people say, well, I can design around the environmental hazards and get the higher productivity. Okay, so that's enough on those types of flames. Let's talk a little bit about heating with different types of gases. MAP gas is a registered trademark, and that was the one in the yellow container, and it has a higher heat intensity than propane, and I demonstrated that. But it doesn't have a higher heat intensity than acetylene. And so if you go to a welding show or something, there will be people selling MAP gas, there will be people selling acetylene, and they're in competition with each other, and they'll both say that they have the better material for welding and cutting. And the question is, who's right? Well, it depends on what you're doing with it. If you're trying to melt steel, as in welding, it turns out the combustion intensity is proportional to T squared. The useful heat is the heat of the flame minus the heat of the melting temperature of the metal that you're trying to melt. If I'm talking steel, this is going to be something like 1500, 1600 degrees centigrade. The adiabatic flame temperature of acetylene is 3100 C. Adiabatic flame temperature of MAP gas, C3H4, is about 2870. There's only a 230 degree difference in the adiabatic flame temperature, but how significant is that? If I take this quantity, the difference in temperature, and I can only take the sensible heat above the melting point of the steel, the heat below the melting point of the steel might bring it up to the melting temperature, but it doesn't melt it. It's only the heat above that actually has the capability of exceeding the melting temperature. And so it's 3100 minus 1600 squared, or 1500, whatever number I use, is 256. I must use 1500 because it's 256 times 10 to the fourth, and 2870 minus 1500 is 188 times 10 to the fourth. So if you look at it, for melting steel, acetylene has 36% advantage because of the T squared advantage. If I was doing some higher melting metal, then acetylene would have an even more significant advantage. And welders who actually are trying to weld steel have noted that in fact they can weld faster with acetylene than they can with MAP gas. And so if you're selling MAP gas, you say, oh, it's just the same, it's absolutely the same. The welders know you're lying. It's not exactly the same. There's a 1/3 advantage with using acetylene rather than MAP for welding. Not necessarily for cutting, okay? And we'll get to cutting, we haven't talked about the process, but MAP has distinct safety advantages. What are the safety advantages? Well, one of the problems with acetylene is that if you try to compress it at 50 psi or something like that, it goes boom. It compresses it under pressure. It will spontaneously decompose, and when it does that, it lets out a little explosion. And so people don't particularly like that. And so if you go to an acetylene cylinder, you can't take a cylinder of gas, of acetylene gas, and pressurize it to 500 psi. In fact, you're not supposed to pressurize it to more than about 10 psi. In fact, most torches are designed for about 3 to 5 psi as the proper acetylene pressure. Doesn't matter what the size of the tip is, they designed it so the incoming acetylene should be at 3 to 5 psi. This is an acetylene cylinder, but you're not just storing gas here at 10 psi because you'd have all of about 60 seconds worth of gas used out of a cylinder like this. It turns out an acetylene cylinder, if you look inside, is actually filled with a very porous material, in this case a white material, which is calcium silicate. It's about 92% porous. They used to use asbestos fibers in the days before getting rid of asbestos, and they used different types of porous materials, but some French scientists in the early 1900s learned that acetylene will dissolve to very, very high concentrations in acetone. And so basically an acetylene cylinder is a tank of acetone, liquid acetone, and they just put the porous material in here to keep the acetone from sloshing around. And also, if you ever got a flame back in there, this acts as a flame arrestor. But calcium silicate, basically a very special type of sand, which they've been able to foam in here to a very light, 92% porous. The rest of it's filled up with acetone, and then you dissolve the acetylene at low pressure, relatively low pressure, like 20 psi, will dissolve enough acetylene in a liquid that you'll have as much gas as if you pressurized it to probably the equivalent of 1,000 psi, which you can't do because it would decompose on you before you got there. But you can dissolve a lot of gas in liquid. You know that because if you've ever opened a Coca-Cola or a Sprite, you see all the CO2 bubbles come to the surface, right? And there'll be a lot of bubbles that come forward. And they haven't even gotten close to putting in the maximum amount of CO2 in water when they do that. So up here is just a little piece of felt, which kind of keeps any of the particles from getting up and contaminating, getting up in the torch. This is what we call the B cylinder, and it stands for bus, because this was the headlights on the bus back in a few years ago. And since I couldn't find Jefferson's Welding Encyclopedia last week, I asked my secretary to order it. It came in yesterday, and so here's the stories out of here on acetylene. Acetylene gas was discovered by Edmund Davy, which I think was Sir Humphrey Davy's brother or something, in 1836. But it was not until 1862, when Wohler's discovery that acetylene gas could be produced from calcium carbide, that the gas became well known. Now I talked about calcium carbide. You just dribble water on calcium carbide and it produces acetylene and calcium hydroxide. These developments were of little consequence, however, until 1892, when Thomas L. Wilson of Spray, North Carolina, which is somewhere down Halifax, Wrightsville Beach or somewhere area, invented a process for producing calcium carbide and established facilities to produce it. And that's where he basically put limestone and carbon in a furnace, in an arc furnace, and synthetically produced calcium carbide. And he didn't think it was useful. I read somewhere else, it wasn't in here I guess, where he basically took it out and threw it in the river to dispose of it, and the river caught fire, and he thought, that's curious. Now, somewhere else in here. Oh, acetylene cylinders, it's got a picture of a cutaway of one of those. Until 1904, no suitable acetylene container had been developed. The gas was used mainly for illumination and was generally piped directly from generators to the area to be served. I'll talk about generators in a second. In that year in Indiana, P.C. Avery displayed to two of his home state's most famous promoters, James Allison and Carl Fisher. Anybody have any idea what Allison and Fisher later did, or who they later worked for?
General Motors.
General Motors. Allison, Detroit Diesel Allison and Fisher Body. Okay. A portable cylinder containing acetylene gas designed to power auto headlights. Then engaged in auto sales, Allison and Fisher were immediately interested, and with Avery set up a small factory in Indianapolis to fabricate the tank. The shop was known as Concentrated Acetylene Company until Avery withdrew in 1906. The company then formed the Presta-Light Company, the forerunner of the Lindy division of Union Carbide. So they're basically taking the calcium carbide of this Thomas, what's his name? Thomas Wilson of North Carolina. Allison Fisher devoted much of the time relocating into the plant into progressively larger quarters. Not until 1910 did they build one of sufficient size in what was then suburban Indianapolis, across the street from the site of the famed Motor Speedway they later constructed. So these guys were the guys who built the Indianapolis 500 Speedway. And that's why the home of Detroit Diesel Allison is Indianapolis. Carbide production continued to increase, et cetera, et cetera. And then in 1897, French team Claude and Hess demonstrated the value of acetone to dissolve the acetylene. Now, today they still produce acetylene in quantity by having calcium carbide. And you just have a big tank, it's sealed, and you put the calcium carbide in the tank, you dribble water on it from a little drip faucet, and the acetylene comes off, and you take that off and you can pipe it around a shipyard or whatever. In the old days, it said in here, the street lights before Edison and Westinghouse and incandescent lights came along, they were using acetylene as the gas for street lights because it burned brighter. They used it as headlights on those little B cylinders they mount on the front of a bus or an automobile. Well, every now and then in Boston, they will uncover some of the old gas pipes from the 1890s and early 1900s. Some of those early gas pipes, have I already mentioned this, were made out of wood. Okay, they just take a big tree and they gun drill it. So you might have a 6-inch log and you'd have a little 1-inch hole in that log down the center, and you kind of stick these together. You might lose a little gas at the seams, but who cares, right? Basically, this was how you had a central generator and you pipe the gas down the street. Some guy would come along and he'd light the thing at sundown, and midnight or 6 a.m. depending on whether you wanted the lights all night. He'd go and snuff out the thing and turn off the valve so that the acetylene didn't keep flowing. So that's how they had the street lights back then. In a shipyard, they still basically don't have great big cylinders of acetylene. They basically pipe the acetylene around, and they just dribble the water in a carbide generator and pipe it around. I remember one shipyard, one of the guys told me a time that he was sitting there working at his desk, and he heard the fire siren, and it was far enough away from where he was. He wasn't too worried about it. Another engineer came in and said, "Oh, they've got a fire down at the carbide shack." And he jumped out of there, that welding engineer jumped out of there as fast as he could to get there before the fire department started putting water on the carbide shack. Okay? Because it's actually real exciting if you start to put out a carbide fire or fire around carbide with water, because you generate more fuel. Unfortunately, he got there, although the fire department should have known, but you never quite know exactly what people are going to do. And he got there in time to keep them from doing it. One of the stories I was going to tell you something else on acetylene, but I don't remember right now. So acetylene is still used. It has an advantage for welding, but it doesn't necessarily have an advantage for flame cutting. Now, flame cutting is an interesting process in that you already saw laser cutting, where you actually use a pure oxygen jet to burn through the metal. Well, it turns out that what you're doing is you're using the steel itself as the fuel. And in this case, the oxygen you'll heat up the surface of the steel to the point where the surface oxide just starts to either crack up or melt. So if we're talking carbon steel, it turns out the melting point of iron oxide is 1380 centigrade. The melting point of the steel is like 1536 of pure iron. And if I bring in a torch that has little pilot flames, oxyacetylene or MAP gas flames, and I put it down on there and I get the surface oxide hot enough, I then have a center jet of oxygen that I have another valve on, another handle on my torch, and when I close that other handle, I get a jet of pure oxygen right down the center. So the jet of pure oxygen hits the hot iron oxide, and the hot blows inside. Now I have hot steel in the presence of pure oxygen at 1400 degrees centigrade. Well, that's going to react, and it's going to generate its own heat of reaction of iron forming iron oxide. And that heat's going to heat up the steel underneath it. It turns out that if I do this properly, and I have really pure oxygen, there is no gas boundary layer. Because the gas that's coming down there gets condensed to iron oxide. I'm creating a vacuum, if you will. If I were to take a closed cylinder of iron and fill it with oxygen and ignite it in some way, I'd end up with a vacuum, right? So I'm condensing away my boundary layer if I do this properly. And therefore, with no boundary layer, the combustion intensity actually reaches a theoretical value of around 100,000 watts per square centimeter. It's more intense than an arc by about a factor of 10. It's about 100 times the intensity of a typical oxyacetylene flame. One of the requirements is the metal oxide must melt below the melting temperature. That's great for iron, and the advantage of iron here is it's 95% of all metals made. So that's a pretty important process, is oxyacetylene cutting or oxy-fuel cutting. You don't have to use acetylene because all you're doing is to preheat it. You can turn the flame off after you start the oxygen jet. In fact, in a steel mill, when you have hot steel coming out of a casting machine that's solidified, and it's still about 1300 degrees centigrade, they don't even preheat it. You don't need to preheat it, it's already heated. They just go with an oxygen lance, and you just take the oxygen lance and blow the pure oxygen on the steel, and you can cut right through the steel. And that's exactly how they cut off the great big blooms coming out of a continuous caster. They just have an oxygen lance blowing pure oxygen on it, and just burns its way through. This is sometimes called burning steel, and literally it is burning the steel. You're using the iron as the fuel. Now, you can't burn aluminum because the oxide melts at a higher temperature than the metal, and so you can't blow it away. You can't burn magnesium for the same reason. Chromium, or stainless steel, which contains a fair amount of chromium, you cannot oxyacetylene cut or oxy-fuel cut because the oxide melts at too high a temperature. Now, titanium, in theory, you should not be able to cut, but in fact, we can. This is a piece of flame-cut titanium, and the other thing I'll pass around, which get towards the end of the class, I'll save some of those others and show you plasma cutting on Monday. But this is a flame-cut titanium. Turns out titanium dissolves its oxide fast enough you can actually flame cut it. And it creates all kinds of smoke and other things. This is actually American Welding Society shows you the quality of flame cut edges you can get on steel. That's basically a comparator to tell you what a good flame cut edge. I've seen flame cut edges better than that, and I've seen flame cut edges that are smoother than the best saw cut you can imagine. So flame cutting is a very rapid, very economical way to cut steel, carbon steel, but not all materials. In fact, it's difficult to cut most of the other materials by just straight flame cutting. But we can do plasma cutting. Or actually, this was laser cut, and I'll pass it around tomorrow or Monday. This is stainless steel, about a ½ inch thick. It's plasma cut. Plasma cutting, I'll describe next time, is basically a form of a jet burner using electric arc, where you basically ignite the arc in a closed chamber and you shoot out a high velocity jet of very hot 10,000, 20,000 degree gas, which basically just melts to the surface. And it turns out plasma cutting is replacing much of the oxyacetylene cutting just because it's become more efficient because of the equipment that people have built. It has other certain advantages, but oxyacetylene cutting is still widely used. I have 2 outfits in my garage, okay, if I need to go burn down my neighbor's fence or something like that. Or if I need to get into some locked building or something like that. You know, just burn your way through, right? And you've seen all that type of stuff in the movies and stuff, people oxyacetylene cutting. Very, very efficient process. You can oxyacetylene cut steel. Well, the thickest I've ever seen is 36 inches. But I've heard about 48 inches and 60 inches of steel being cut. Now, most people don't have to oxyacetylene cut something that thick. But it's just a jet of oxygen burning through the hot steel at a very high rate of speed, giving tremendous power densities. Okay, so that's enough for today. We'll finish up on flames and start arcs on Monday.